Hey folks, so this is a short video about section, this actually should be section 5.5 in the book about right triangle trigonometry. So in the previous video, we introduced the functions sine, cosine, and tangent, and we saw that they're closely connected with right triangles and circles. And so in this section, we're just going to sort of leverage that to solve some simple geometry problems, essentially. So this is a review from that video. We discovered that if you put an angle theta in a right triangle, like you see here, that the cosine of the angle, and this can be any right triangle now, so the big triangle here is not necessarily in the unit circle. We've labeled the sides x, y, and r. So r is the hypotenuse and x and y are the legs. And we found that cosine is equal to x divided by r, the hypotenuse, and the sine of theta is y divided by r, the hypotenuse. So if we simplify this picture a little bit, I think that's here. Whoops, that's not a simplified picture. Where's the picture? Here it is, down here. So let me get the picture first, and then I'll talk about that text. If I simplify this picture, so I'm just going to throw out the purple and the blue sides here and just focus on the big triangle, and I'm going to relabel these sides a little bit. So R is the hypotenuse, right? That's opposite the right angle. So I'll just call that hypotenuse. And then we'll call Y the opposite side because it's opposite the angle theta over here that's in the spotlight, right? So that's the opposite side, and we'll call X the adjacent side because it's kind of next to the angle theta here in the spotlight. And so we get this picture. So again, this is really the same triangle from up above. We've just relabeled the sides. And if I plug those labels into our equations, right, cosine is X divided by R. So that's the adjacent side divided by the hypotenuse. The sine was y divided by r, so that's the opposite side divided by the hypotenuse. And the tangent is the quotient of the two. It's sine divided by cosine. And if you put sine over cosine, the hypotenuses cancel and you just get opposite over adjacent. So I imagine you may have seen these things before. If not, that's fine too. Some people use the acronym SOHCAHTOA to remember this, right? So that's S for sine, O for opposite, H for hypotenuse, C for cosine, A for adjacent, H for hypotenuse, T for tangent, O for opposite, A for adjacent. But in a remote class like this, memorization really isn't an issue, so that's not such a big deal. You can always look up these relationships if you need them. Okay, so this is really all we'll need to solve some of the problems that we want to solve. So let's take a look at the first problem that we want to solve. Here it is. It is exercise 530. So here I have a right triangle, and all I want to do is find the sine, cosine, and tangent of alpha. So this symbol down here is the Greek letter alpha. I'm just changing the label on the angle a little bit. You can see the right angle is marked, right? So when you see this little square, and like the one on the lower right inside a triangle, that's indicating that that's a 90-degree angle. All right, so let's try to find these values. Sine is just going to be the opposite, which is 8 divided by the hypotenuse. Now you'll notice that we don't know what the hypotenuse is in this picture, but it's a right triangle and we know two sides, so we can use the Pythagorean theorem to figure out the other side. Right, the length of the hypotenuse just satisfies, if I call it C squared is 8 squared plus 14 squared, right? 8 squared plus 14 squared are the other two sides. And when I do that math, I come out to 260 for the value of C. Okay, so that means that the sine of my angle is going to be 8 divided by, not 260, but the square root of 260, of course, because I want C and not C squared, right? So when I take the square root here, I get about 16.12 on my calculator. Okay, so the sine, again, is opposite over hypotenuse. That's 8 divided by 16.12, which comes up to 0.496. The cosine is adjacent over hypotenuse, so the adjacent was 14, right? So that's going to be 14 divided by 16.12, and that comes out to be 0.868. Sine and cosine will always be between -1 and +1, and that's because, remember from the previous video, These things are coordinates of a point on the unit circle. And if you're on the unit circle, then your coordinates are always between -1 and +1. Okay, finally, the tangent here will be opposite over adjacent. We don't even need the hypotenuse for that. That's just 8 divided by 14. All right, so this is just kind of straightforward exercise to get used to calculating sine, cosine, and tangent. Tangent does not have to be between -1 and 1. It comes out that way here, but tangent can take on actually any value potentially. All right, let's try the next one. So here I have another triangle, and a couple of the features of the triangle are labeled. So this side in the upper left is 12. I have a 62-degree angle down here, and you can see in the problem it says the angle at C is a right angle. So that's the angle at the top of the triangle. Well, notice that if I know that that's a 90-degree angle, and then this one down here, of course, is a 62-degree angle, then I can figure out the other angle because they have to add up to 180 degrees. And that may be the easiest thing to do first. So let's see if we do that first. Yes, the unmarked angle must be this quantity, right? The angles have to add up to 180. So 90 plus 62 is 152. And that means the other one has to be 28 in order for them to add up to 180. Okay, so this is a 28-degree angle, and now I can use sine, cosine, and tangent to figure out the values of A and C that are missing. Remember, this is a right triangle, and the right angle is up here at the top. So there are multiple ways of going about this. One way is to use the 62-degree angle and the side length 12. I could also have used the 28-degree angle, right? So if I use the 62-degree angle, then 12 is the opposite side, right? Because it's opposites the 62 degrees. So that means the sine of 62 degrees is opposite over hypotenuse. That's 12 over C. C is the hypotenuse, right? Because it's opposite the right angle. So that gives me this equation. Sine of 62 degrees equals 12 divided by C, and I can solve for C, right? I just multiply both sides by C, and I get that, right? So I multiply both sides by C, and now I divide both sides by the thing multiplying the C. This thing is just some number, right? It's whatever the sine of 62 degrees is, and I'll be able to figure it out on a calculator. So I go ahead and divide both sides by the sine of 62 degrees. I plug this thing into my calculator and I get 13.59 as a value for C. And if I look at my picture, yeah, that looks reasonable, right? If I got a value of C that was like, 500 or something like that, I would be skeptical that something went wrong. Okay, now I want to find the value of A. And again, there are multiple ways to do this. Let's see which way I decided to do in these notes here. There are multiple ways to find A. That's what we just said. One way is to use the tangent function, right? So if I again focus on 62 degrees, the tangent of this will be opposite over adjacent. So the opposite side is 12, we said that before. The adjacent side will be A, right? C is the hypotenuse, so that's neither opposite nor adjacent. So that gives me this equation. Tangent of 62 is 12 divided by A, and again, I can solve for A. I'll just multiply both sides by A first, and I get that. This tangent of 62 degrees is just some number, so I'll divide both sides by that number, and I get this, right? 12 divided by the tangent of 62 degrees, and on my calculator, that comes out to be 6.38, and that looks reasonable. Another way to find A, of course, would have been using the Pythagorean theorem. If I know this side is 12 and I know this side is 13.59, because that's what we figured out. Is that what it was, 13.59? Yes, that's right. Then I can use the Pythagorean theorem, and you should get the same number as we got here, 6.38. So that's a good exercise to try now. Use the Pythagorean theorem to find A and see that you get exactly the same thing. Okay, let's try another exercise here. So 5.32, and I think I have the text of it here, so we don't have to keep going back and forth. So we have a 26-foot ladder leaning against a building, and the angle between the ground and the ladder is a fairly steep 75 degrees. And I want to know how high the ladder reaches up the side of the building. Okay, when faced with any word problem, a good thing to try is to draw a picture. So some problems don't lend themselves well to pictures, but if you can draw a picture, it's almost always a good idea. And here we can draw a simple picture. Here's the picture, right? So I got my ladder, right, leaning against the building over here, and then the ground, of course, runs horizontally. And so this length B over on the right, that's the height that I'm looking for. Now, an assumption we're going to make here that's not stated in the problem, but seems reasonable, is that the building is square, so it and the ground meet in a 90-degree angle or very close to a 90-degree angle. So this is a right triangle, and I can use trigonometry to figure out the value of B. Now, B is the opposite side from 75 degrees, and 26, of course, is the hypotenuse. It's opposite the excuse me, right angle. And so that suggests the sine function would be a good thing to use here because the sine of 75 is opposite over hypotenuse. And I get this little equation, sine 75 degrees equals B over 26. So if I multiply both sides by 26, I get that, right? This is similar algebra to up above. Sine of 75 degrees is just a number, so I divide both sides by sine of 75 degrees, and I use my calculator, and I get 25.1. And that looks reasonable for B. Notice that if I got, say, B equals 28, I would be skeptical because the hypotenuse of this triangle is 26, and that's the longest side. So I'm not going to get anything bigger than 26. It's almost 26 because 75 is a pretty big angle, right? Remember, this couldn't possibly be bigger than 90 degrees if it's going to be inside a triangle. All right, so here's another similar example. We'll do a couple more of these, I think, and that'll be good. So here's the situation. Right, the angle of elevation to the top of a building is found to be 3 degrees from the ground at a distance of 1.5 miles from the base of the building. So if you are a ways away from the building and sort of sighting to the top of the building, that's a fairly small angle of elevation because you're far away. And I want to know what the height of the building is. Okay, so what do we do first? Well, good first step, draw a picture if you can. And here again, I have a picture that's really very similar to the one up above. Instead of a ladder, this is just my line of sight now, this diagonal line at the top. The angle is 3 degrees, right? So this is the ground along the bottom. Here's my building over on the right. The distance from where I'm sighting to the building is 1.5 miles, and I want to find the height of the building B. Okay, well, B is opposite the 3 degrees. 1.5, notice, is adjacent. Again, we're going to assume that the building and the ground make a 90-degree angle. So the hypotenuse is this long side over here on the top. But I don't think I care about that here. I'm going to go ahead and use the tangent function, right? Because tangent of 3 degrees is opposite divided by adjacent. So that will give me an equation that involves the thing I'm trying to solve for, right? Tangent of 3 degrees is B divided by 1.5. I want to solve for B. So first I'm going to multiply both sides by 1.5 to get rid of that denominator. And I get this. And I'm all set. I can just do that 1.5 tangent 3 degrees on a calculator and get my solution. And I come out with 0.0786. Notice that that is in miles, right? Because 1.5 was in miles. So it's 0.078 miles. That's a little bit of an odd way to describe the height of a building. It's correct, but we don't usually talk about building heights in miles. So to convert to feet, remember that there are 5,280 feet in a mile, or Google the fact that there are 5,280 feet in a mile. And so if I do this unit conversion, right? So notice when I take a united value like this, I can multiply by fractions with different units. As long as the quantities are the same top and bottom, I'm multiplying by 1. 5,280 feet is equal to 1 mile. So that blue fraction is equal to 1, and multiplying by 1 doesn't change the quantity any. Miles will cancel, right? I have mile in the numerator and the denominator, and I'm left with feet. And if I do this on my calculator, I come out with a 415-foot building, pardon me. Okay, One more example, and then this is a pretty short video. And after you get through this, I do recommend doing some of these other ones in the notes and exercises, and also you can see there's a number of other ones here, and also in the book to sort of practice this. So here is the situation now. I have a tower located 400 feet from the building, and I am now in the building somewhere looking out a window. And from my line of sight, I have an angle of elevation to the top of the tower of 36 degrees and an angle, what they call an angle of depression. So that's the angle down to the bottom of the tower is 23 degrees. How tall is the tower? So again, first step, draw a picture if you can. And the picture here looks like this. And if you like, pause the video here and try to draw this picture yourself and see if you come out with something similar. Okay, this is what I come out with, right? So here is where I am, where the cursor is, looking out the window of the building, and I look up to the top of the tower, and I look down to the bottom of the tower. I filled my angles in, right? The angle of elevation is 36 degrees. The angle of depression is 23 degrees. 400 feet is the distance from the building to the tower. So it is the length of this not dashed horizontal line that goes straight across. I want to figure out how tall the tower is, and I'm going to do that in two parts. First, I'm going to figure out how high this lower portion is. Then I'm going to figure out how high this upper portion is, because I have two right triangles here, right? This bottom triangle where the cursor is now, or I guess it's a middle triangle, and this top triangle where the cursor is now. Okay, so I'm not sure which one do I do first here. So, okay, let's do the top first. So I'm going to call this top portion here, the length where the cursor is moving now, T, and that is opposite the 36-degree side. The 400 is adjacent to the 36-degree side, so that suggests that the tangent function is a good one to use because tangent is opposite divided by adjacent. So the tangent of 36 is the opposite value, T, divided by 400. And we've seen a few of these kinds of equations at this point. I'll multiply both sides by 400 to solve the equation for T, right? And I come out with this value. This is going to be in feet because the 400 was in feet. So let's add that here. Okay, and this I just did on my calculator. Now this isn't the height of the tower. This is just the height of the top part, the value of T. So if I let B be the bottom part of the tower, right? So now that's the part down here. That is opposite the 23-degree angle. And I know the adjacent side is 400, right? The dotted lines are the hypotenuses of the triangles. So we're not using them in this particular example. So again, I'll use the tangent function. The tangent of 23 is going to be the opposite side, which is B, divided by the adjacent side, which is 400. I get a very similar equation to what we got up above. So I'll multiply both sides by 400 to get my value of B. There we go. Right, and use my calculator, and I come out with this. And again, that's in feet. Okay, well, I'm basically done, right? I know how tall the top part is. I know how tall the bottom part is. I just have to put them together to answer the question and figure out how tall the tower is. And the height of the tower comes out to be this, right? 290.6 plus 169.79. A quick word before we close out this video on using your calculator to compute things like that, for example, 400 times the tangent of 36 degrees. A minor issue here is that we can measure angles in degrees or in radians, and the value will come out differently when you enter it on a calculator, depending on which units you use. So be a little bit careful about this. On Google's calculator, you can see up here in the upper left, RAD stands for radians, DEG stands for degrees. Whichever one of these is darker, that's the mode that you're in. So right now I'm in degree mode. If I click on rad, now I'm in radian mode. So if I want to do this calculation, 400 times the tangent of 36, first I'm going to make sure I'm in degree mode because that's the way the angle is measured. And then I'll do 400 times, and you can see I have, there it is, tangent of 36, close parentheses, equals, and that's where I get the 290.62, right? If I had done this in radian mode, I would get a different value, right? So let's switch to radian mode and try the same calculation. 400 times Tangent, there we go, 36, close parentheses. You can see I get something very different from the 290 or so that I got before. So be careful of this. Every calculator is a little different in terms of how they do these modes. So if you're using your calculator, make sure you know which mode you're in, how to switch modes, and make sure you're in the correct mode when you do a calculation. And on Google Calculator, again, this is how you switch mode, is just by clicking on radian or degree. Okay, that is good for this section. Again, please do some of the practice and the notes and exercises in the text and take good care of yourselves.